Hello, my name is Elizabeth Fox. This is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology. The title of my talk is A Bayesian Model of Capacity Across Time. I'll start off by describing the capacity coefficient. It describes one's efficiency to integrate multiple cues compared to the performance of an efficient cognitive model. We can use the capacity coefficient to investigate questions such as how well do humans integrate audiovisual information or multispectral information. In addition, the capacity coefficient offers a common metric to compare across different contexts, such as one's efficiency to process multispectral images and two different methods of displaying the information to the user. The model of efficient performance assumes the participant has the processing resources necessary to accommodate multiple sources simultaneously. That's unlimited capacity. The process of each source does not facilitate or inhibit the processing of the others, independence, and each source is processed simultaneously or in parallel. Together, the baseline assumptions form a USIP model, estimated by the combination of the processing time of each source in isolation. When participants respond after one source finishes, capacity or, and each source is context invariant, then we can simplify the USIP model to the minimum processing time of each source in isolation. The minimum of two random variables is calculated as their sum of their cumulative hazards. That's the H of T. And the cumulative hazard of an observed response time indicates the amount of processing completed up to a given time. Therefore, the USIP prediction of an OR process is defined here. The capacity coefficient is then the ratio of the observed performance when all of the sources are present to the USIP model prediction. If capacity is 1, it's classified as unlimited, meaning all of the USIP assumptions are met. Deviations from 1 occur if one or more assumptions of the USIP model are violated. Capacity less than 1 refers to a limited capacity and can occur if processing each source is slower with more sources presented due to a limited attentional capacity, or if there's inhibition among the processes, or if the process is serial rather than parallel. A capacity greater than 1 is supercapacity and implies that there's better performance than the USIP model, and that could be due to facilitation between processes, including some coactive process. So for instance, we compared performance with both images, either presented beside one another or combined algorithmically, to a USIP model prediction using the performance with each image type in isolation. In these data, we found both were less efficient than the USIP model would predict. However, we can compare the two display types to see that the blue, which is cognitive fusion, was higher than the red, which was algorithmic fusion. And in a second experiment, we demonstrated that with training, capacity changed across 8 sessions. Specifically, although response times and accuracy increased, capacity decreased for both display types, cognitive and algorithmic. Because we found more limited capacity across time and response times with multiple sources are relative to the baseline, we could conclude that training improved efficiency with single images more and at a faster rate than the information from multiple images together. In most applications of the capacity coefficient, the analyses assume stationary performance across time. However, in many contexts, participants' performance might vary across time. For example, a vigilance decrement or training. A time-varying capacity measure would be valuable to determine the nature of the change over time, but dropping the stationary assumption results in a severe loss of power. A corresponding parametric measure of capacity will increase the power of our estimate with fewer samples. The capacity coefficient relies on the combination of response time distributions. Response times have a similar underlying distribution properties to the Weibull distribution, and that's often used to parametrically describe survival data. So in this model, we assume our data approximately follow the shape of a Weibull distribution with 2 parameters, shape, so that's beta, and scale, which is theta. The beta parameter can be interpreted as the shape such that for beta greater than 1, response rates increase as a function of time, beta equal to 1, response rates are consistent regardless of time, and beta less than 1, response rates decrease as a function of time. The theta is interpreted as a scaling parameter. Therefore, we can use this model to estimate the function for each source, so that's each I in this equation, of information, with unique shape and scale parameters that approximately characterize single source performance and performance when all sources are presented. We can take the sum of the hazards estimates of the Weibull across all sources, so that's each n, to form a parametric USIT prediction, and use the capacity or coefficient to capture how performance with all sources of information present change relative to USIT model predictions. Bayes' theorem offers a way to update our estimate of capacity given new observations across time. We can calculate the posterior distribution of the model parameters using a combination of a prior probability and likelihood function. The prior probability function represents our belief about the data before taking into account any observation. For our purposes, the USIT model serves as the prior belief about information processing efficiency. The likelihood function is estimated using our observed data. To simplify estimation of the shape and scale parameters, we chose a conjugate prior. A conjugate prior provides a closed form expression. Therefore, calculating the distribution requires much less computation. The Weibull function with a known shape belongs to the exponential family. Therefore, a conjugate prior does exist. And the conjugate prior of the scale parameter for our Weibull function with a known shape is an inverse gamma distribution with parameters a and b. And in this context, I'll refer to a and b as hyperparameters to distinguish those from the model. We use the conjugate prior and the likelihood of the observed data to calculate the hyperparameters of the posterior. Our posterior distribution is the normalized product of the prior and likelihood, and it has the same algebraic form as our prior. The relationship of the prior to its conjugate prior means that we can use the mode of the posterior to estimate the scale parameter of the Weibull distribution. I mentioned we use a time-varying Bayesian update. Here, we can weight each sample in the likelihood update based on the recency by which they occurred. We obtain posterior estimates for both the prior and likelihood, such that the number of samples added to the posterior is the sum of the weights, and each sample of the likelihood is weighted by some drop-off function based on the recency of the response times. The time-varying model provides temporally precise estimates of capacity and might offer useful information for online software, such as an adaptive automation. We draw samples from this posterior Weibull to represent performance after each trial. And using these updated estimates for each of these terms, we can then estimate capacity on every trial. It's important to note here that because we are assuming the shape is constant, we can simplify capacity to a single estimate across all times for a given trial. There are numerous options for the choice of the likelihood filter to allow capacity to be non-stationary. In this application, we weight the contribution of the data to the likelihood by how recently they occurred using a squared exponential smoothing function. So it looks something like this. First, I simulated response times that would suggest unlimited, limited, and supercapacity processes. We deliberately then stitched them together from those distributions to form a sequence of response times such that capacity changed from unlimited capacity to supercapacity to unlimited capacity to limited capacity. We apply the model to obtain an estimate of capacity for every trial. The dashed line is the USIT model performance, so capacity equal to 1. This blue line is a single estimate, estimating unlimited capacity performance across the entire stitch sequence of data. So this would be a non-stationary, this would be a stationary estimate. Now we use our time-varying Bayesian model of capacity. And the bold line is the estimate of the lighter black lines in the 95% highest density interval for each trial estimate. The model captures the variation that we stitched together, but due to the weighting function and the weight given to the prior, it does not slowly adapt. Specifically, you can see that in the transition form, unlimited to super and super to unlimited. So those data were based on a model using a smoothing parameter for the likelihood filter of 80, meaning that the proportion of the response times were used up to 80 trials back. However, we can change the smoothing parameter to adapt and increase temporal precision of the estimate. Because we're using a parametric model, we could obtain reliable estimates with relatively few trials. With a smoothing parameter of 40, we can see the model adapts more quickly, but this also introduces more uncertainty of the estimate. So you see that in the larger 95% HDI. Similarly with the smoothing parameter of 20 and 10. So here we can see that for these data, the appropriate smoothing parameter for the likelihood filter may fall between 20 and 40 to balance temporal precision and uncertainty of the estimates. Another parameter set by the modeler is the weight given to the prior. Here, because we update the prior to learn about an individual's performance across time, we can see that the more weight given to the trained prior increases precision of those estimates. So after demonstrating the usefulness of the model with simulated data, we want to illustrate how the model characterizes human data. Stepping back to the beginning of the talk, I talked about the processing capacity of two different multispectral displays. Using our adaptive Bayesian parametric model, we investigated whether capacity changes not just between sessions, but within a session. For this application, I fixed the prior weight to 20 and showed the results of one subject in their first training session across the same four choices of smoothing parameters for the likelihood filter, 80, 40, 20, and 10. Generally, you can see that we find the estimates of capacity are stable across time. With a steeper likelihood filter function or a more temporally precise estimate, there was little variation in some times during the session. But mostly, this participant's efficiency to combine multispectral imagery presented side by side did not vary much within this particular session. Now, fixing both the parameters for the weight and the likelihood filter, we compared variation in this subject's performance in one session across the two different display types. Overall, we found performance did not vary too much for either display method within that first session, and generally algorithmic fusion was less efficient than side by side. So to summarize, in this work, we derive and illustrate an adaptive Bayesian model of capacity coefficient to investigate processing efficiency in contexts where participants' performance might vary across time. Our conjugate prior was updated by weighting the observation contribution to the likelihood by how recently they occurred. We demonstrate the approach with both simulated and human data and how the choice of model parameters may influence the temporal precision and variability of the estimates. In this application, we made a couple of modeling choices. One was to use the squared exponential function for our likelihood filter. In future work, we'd like to investigate how other filters, such as linear exponential, may influence our results. Lastly, in these human data, we did not find efficiency varied within a session. However, we believe the time-varying capacity coefficient will be a valuable tool for measuring phenomena such as the vigilance decrement. We would like to collect data or collaborate with you to analyze data where efficiency is expected to change across time. Thank you for your attention.